projection at any angle. So let's say that this is horizontal ground, and this is the path that our particle is going to take. This is the greatest height that it reaches above the horizontal surface. This is the range, which is the distance that it travels until it first hits the ground over here. So if we've got the particle here, and we know that the acceleration due to gravity is vertically downwards, then we have an initial horizontal component and an initial vertical component to the velocity. When the particle has travelled a bit, the horizontal component will be the same because the acceleration is all vertically downwards. So the vertical component will be smaller. As we move further up, again the horizontal stays the same, but the vertical gets smaller. When we get to the top, the motion is all horizontal instantaneously. So at the greatest height, the vertical component of velocity is 0, and that's often how we can go about finding the greatest height. When we get to here, the horizontal component once again is the same, but because we're accelerating downwards, now the particle is travelling downwards. And then it hits the ground here. At the horizontal range, the vertical component of displacement is 0 because it's back at its initial displacement, and that's often how we go about finding the range. Let's call the time it takes to get here t. T is known as the time of flight. With the model we are using, no air resistance, etc., the greatest height happens at half of the time of flight, so it will be t/2 when it's here. If air resistance is included, the path is no longer symmetrical, and a realistic object would probably travel more in a path like this. But that's not what we're going to be dealing with here.